welcome to a presentation from Daniel Honerkamp from the University of Freiburg on learning kinematic feasibility for mobile manipulation.
Yes, let me just share my screen.
Yeah.
Can you see it?
Not yet. Yeah, there we go.
Perfect. So, yeah, glad to be presenting here. I'm Daniel from the University of Freiburg. And yeah, I'll be talking about our approach for mobile manipulation, which is joint work here at the University of Freiburg with Tim and Abhinav. And so why mobile manipulation? In general, this remains a critical challenge for autonomous systems across both service and industrial robotics. But at the moment, it's still commonly reduced to sequentially move the base and then do arm manipulations in static settings, finding good base positionings, etc. But many tasks do require us to jointly use the base and the arm to actually complete them, such as the PR2 moving through a door that you can see here. And furthermore, being able to do so generally enables us to come up with more efficient solutions and more efficient operation for many tasks. And we are, of course, not the first ones to tackle this problem. We have a lot of classical planning approaches that can, in general, solve these tasks, but they often struggle with task-specific constraints or require replannings in dynamic environments. We also have things like inverse reachability maps that find good base positionings, and this has also been extended to jointly moving the arm and base in the same settings. But they often require expert knowledge about the platform, finding approximations, and can be overly restrictive. And on the other end of the spectrum, we do have end-to-end reinforcement learning approaches, but oftentimes these result in task-specific models that require to be retrained on each new task. And also these models often struggle with the big joint configuration space of both base and arm, and often have to make restrictions on the action space. So what we propose is to couple things like knowing the inverse kinematics with learning-based approaches. And particularly, we decompose this task into an arbitrary end effector motion generator, which, given a goal for the end effector, shown in green here, produces velocities for the next step end effector motion, and a reinforcement learning agent that controls the base. And the objective for the base agent is, given these motions for the end effector, to find base controls shown in purple that make these motions feasible. So how exactly do we do this? We formulate this as a goal-conditional reinforcement learning problem in which we have a robot state, a goal for the end effector. This end effector planner produces motions, next step motions for the end effector, and the base agent observes these things and then produces base velocities. We then use standard inverse kinematic solvers to solve for the remaining degrees of freedoms in the arm. And we also use this to directly provide a dense reward signal to our agent. And in particular, this is a very simple Boolean indicator whether the next step pose was feasible and some small regularization on the base actions. And this strongly simplifies the learning problem and avoids reward engineering for reinforcement learning. So yeah, as I said, this reward signal is really valuable because it is so simple and does not require additional engineering. But this decomposition also allows us to perform zero-shot generalization to unseen tasks at test time. In particular, it means we can simply plug in other end effector motion generators to solve different tasks. And importantly, producing these end effector motions is now much simpler because it can abstract from most of the difficulty, because the reinforcement learning agent handles the whole aspect of making them feasible. And lastly, we demonstrate that this approach is applicable across many robots with very different kinematics without requiring further expert-based knowledge or adaptations. How does this fit together with MoveIt, or how do we use MoveIt within this? In general, MoveIt allows us to manage the robot state and kinematics. So we have our inputs, base actions, and end effector motions, and we can update our kinematic state with this. In the real world, we can directly integrate the sensor readings from the real world, and then we hand this off to an inverse kinematics plugin, which through MoveIt we can very easily switch between. And in particular, this allowed us to easily move to the bio-IK solver, which is very nice for our approach because it allows us to add additional regularizations to the solutions. So we can directly add cost functions that minimize displacement and produce smooth arm joint motions over time. And then, of course, we can directly execute these motions with the low-level controllers. And also, it makes it very easy for us to specify the whole system on different robots. Basically, all you need is a URDF file of the kinematics, the joint groups that you want to control, and define a base motion that you need. And in particular, we demonstrate our approach across these platforms. On one hand, we have the PR2, which is omnidirectional and has a very flexible 7-degree of freedom arm. The Toyota HSR, which is also omnidirectional, but only has a 5-degree of freedom arm. So it really needs the base to achieve many end effector poses. And lastly, the Tiago, which has a flexible arm, but a constrained motion, a constrained base with a differential drive. So what can we achieve with this system? At test time, we produce tasks representative of the real world for both seen and unseen motions. So here you can see all robots, the PR2, HSR, and the Tiago from top to bottom. And in this case, we construct 3 different tasks. This didn't work.
Says it cannot play media at the bottom. Not sure why.
Not sure if there's an easy solution to this. Yeah. Okay, I'm not sure. So
if you have the video separately, you can launch it in like Windows Media Player or something like that and share that window. That's easy.
Just have to share the window. Yeah, just share the full screen. So, now you should be able to see it.
Yeah, now we can see it.
Yeah. So yeah, from left to right, we have a pick and place task that we construct. We have a door opening task and a drawer opening task. And these are imitated from humans and have never been seen by the agent before. And as you can see on all these platforms, the agent learns meaningful behavior and to control these different kinematics and successfully solve these tasks. Yeah. Okay. And we also test this in the real world, of course. Okay. So we put this on our real PR2 and directly transfer the policy from simulation to the real world, solving pick and place tasks, again, door opening tasks and drawer opening tasks. And we find that it really directly transfers and is able to control this without any further fine-tuning or adaptations. And so now we have a system that can enable arbitrary end effector motions and allows us to easily specify novel tasks and task constraints. What's missing now is to put this into human-centered cluttered environments. And the main thing we're missing here is to incorporate the constraints that come from collision objects. So this is what we're currently working on. We are interested to put this into things like a bookstore that you can see here, or a home apartment, and directly use in these complex environments. We do this by integrating obstacle maps of the environment, and they have some desirable properties for us. Particularly, they promise to generalize very well to unseen objects, as they are purely geometric, and they work with various sensors on various robots. So the reward function now does become a bit more involved, as now we have in general terms to track the end effector motion, to avoid the collisions, and we also allow the agent to control the velocity of the end effector motions. So it can take its own time to avoid objects if it needs to. Yeah, I won't go too much into detail. And we can train this again, striving for simplicity in procedurally generated environments with very simple geometric shapes, as you can see here. And we can produce end effector motions to reach random goals based on A-star planners. And this then results to be able to move in these difficult environments. So, yes. So here we have the HSR robot moving from the center of the room, and its goal is to pick up a cereal box in the bottom left corner, following a specific end effector motion. And again, it has never seen any environment like this. It has never seen any of these objects or obstacles, and directly works with real execution in gazebo. And we'll successfully pick up the cereal box. And you might want to ignore the box dropping down. This is simply the gripper physics in gazebo being specified incorrectly. But its goal is to put down this box on the other table. Which it succeeds to do. And the other nice thing we can do is we can directly avoid dynamic obstacles. So here the goal is just to reach or to follow a motion to a certain end effector goal. And yeah, again, never having seen any dynamic obstacles or anything like this, it is able to directly avoid any of these obstacles, finding reasonable paths and having no such constraints as replanning times. Yeah, so this is our main approach, and hope that gave you a good overview. But given these capabilities, we can now also think further of what this might allow us to do in the future. Of particular interest is to think about if we can incorporate this as low-level policies in hierarchical approaches. Having a very capable base policy already would allow us to avoid the instabilities of jointly learning high and low-level policies, which is one of the main issues in hierarchical reinforcement learning. And it would allow us to now really focus on learning task-relevant long-term behavior. So learning what motions we want to execute with the end effector. Another thing that might be quite interesting is to think about if we can include this in something like task and motion planning pipelines, where a majority of the time is spent on motion planning and collision avoidance. Yeah, and a small note, this is also part of the Open Deep Robotics Toolkit research project, which generally provides a lot of deep learning-based tools for robotics, which may be of interest to some people here. You can find all of these, including our approach, at this link. And that is it. Thank you very much. A short funding note, and you can also find our paper and more details on our project website.
Thanks so much. If people have questions, they can either raise their hand and I'll unmute them, or they can post in the chat. Then you can probably stop presenting. It's a little distracting to look at myself. If there are no questions, I have a quick question. This is really impressive work. I mean, it's kind of, pretty cool to see. One thing I was wondering about is, for instance, for one of the tasks we showed that it was the PR2 opening doors. What's the state space and the action space that you're using for the reinforcement learning part?
So the state space is mostly the robot state, so joint positions, velocities, as well as these obstacle maps, so 2D obstacle maps. And the action space is base velocities, linear, angular, for the omnidirectional base, the velocity of the end effector motion, and in this case, we're also controlling the torso lift joint.
Okay, so they're both quite high dimensional and continuous, right?
Yeah, but that's kind of the nice thing about deep learning based approaches, that we can really learn to make sense of these higher dimensional inputs. The obstacle maps do tone down the problem a little bit because they are comparable to RGB images or things like that. They are a bit faster to learn and a bit less compute intensive to process.
And how long does it take to learn how to open a door?
So right now training is something like maybe 7 to 12 hours.
Okay.
But this is just general behavior, and so we don't train it at all on the door opening task.
Wait,
and this just.
But it seems like there's got to be something specific about door opening, respecting the kinematic constraints, and it's like if you just say move roughly here, I mean that's not going to open a door, right? There's a lot of things.
So it does receive the end effector motions. These are specific to the door opening. Otherwise, of course, it wouldn't be possible. But having to move the base to respect the frame of the door and reacting to the door actually opening, which changes your obstacle map, that works without having seen anything like this during training.
Very cool. I guess I have to read the paper to really understand this. Sounds like maybe Michael has a question about this.
Yeah, so thanks. I actually read the paper some time ago already. I would have prepared it again if I had known that you presented. Sorry. Thanks. I think that's really great work. I have one technical question for you and one actual content question. The technical question is, you have a PR2 running. Who manages that system and what ROS version runs on it at the moment?
Well, we are managing it. So me and one or two colleagues. Yeah, the ROS version is not completely up to date, so currently it's ROS Indigo.
Oh, okay.
So
yeah, I'm asking because I also maintain our PO2 robot, so maybe we want to talk later. But the actual content question for your paper would be, you talk about using the PO2, and then you assign the end effector trajectory for the right gripper, but the PO2 is bimanual, and so are many other robots. So how would your framework generalize to actually using bimanual manipulation instead of just using one end effector?
yeah, that's a very interesting question. I think in general you could definitely use the same approach. It might become a bit more challenging to produce good end effector motions for both simultaneously. So that's probably something to think a bit further about, what exact tasks you
Okay,
want.
but that's not the part I mean, because you train this network based on the input end effector motions, right? So do you think you could train the system to behave well for both end effectors, for more or less arbitrary trajectories on both end effectors? Or do you think that would be too big as a state space to still learn?
I think in general, I don't see a concrete problem to learning this. How hard of a problem it is, you would have to see if you can actually explore the space well enough. So that can become a bit of a limitation with reinforcement learning in continuous actions. So for example, for the Thiago with its continuous drive, it's actually a much harder task to not get stuck in local optima or suboptimal behavior.
All right, we should probably stop here and move on to our next presentation. Thanks again, Daniel, for your presentation. Very interesting.